Hiya, how you all doing? I want to talk to you about vectors today, which is not an easy topic, okay? So just do the best you can with it, all right? And try and pause the video every now and again so you can take notes, okay? I'll give you a good generalization of what vectors are, okay? Right, first of all, the thing to know is that they've got two things. They've got magnitude and direction. Magnitude means size, okay? Let me just give an example with that. If I say that someone is traveling with the speed of 2 meters per second, that's a magnitude. The magnitude is 2 meters per second. If I say to someone who's travelling at 2 meters per second due east, that gives you a direction. Or I could give it as a bearing, okay? So a vector's got both size and it's got a direction as well, okay? Now, give you some simple examples of how vectors work. Okay. See that? That's a coordinate grid, okay, called Cartesian axes, okay? And I've plotted the point A, which is 3, 6, okay? If I want to define how to get to A from the origin, what do? Okay, literally what do I do to get from the origin to point A? Well, you move 3 units towards the right and 6 units upwards. Do you remember doing that in translation work? Okay, you'd have written that as something like this. Okay, the translation is 3, 6. That's what we call a vector. Okay, it describes how to get from point O to point A. Okay, the way we write that, okay, is like this. If I just leave that there for a moment. We write that as from O to A and then an arrow on the top showing the direction. And that symbol is for vector from O to A, okay? And OA is equal to 3, 6. Now, I can show you that on this coordinate grid by just drawing them together like that. Now, drawn like that, that's just a straight line, okay? What distinguishes a straight line from a vector is the direction, and the direction is that way. Because I said from O to A, not the other way around. If it was the other way around, from A to O, it would be different. And I'm sure you could see that the vector would be different. If I went from A to O, it would be -3, -6. Okay, so the direction is quite important. Okay, now I don't need to draw a set of axes every time I think about what a vector is. So the vector from O to A, 3, 6, it means from point O, which I'll label there, I go 3 units towards the right, and I go 6 units upwards, and then my end point is there. And because it's from there to there, I'll put the arrow in to show the direction. That is how we visually represent a vector OA. Does that make sense? I hope so. Okay. So how would you visually represent the vector from O to B if I told you O to B was -2, -4? Well, what you do is you'd start with O, okay, and then you'd have -2, which is that way, 2 is that way. Notice with a length, I don't need to record it as being negative. I'm just noticing the 3 and the 6 and the 2 as lengths, you see. But the negative means it's in the negative x direction, towards the left, and the -4 means in the negative y direction, doesn't it? Downwards. That's 4 units downwards. And from O to B, that's what the vector looks like, okay? So that's really what vectors are. They're useful for describing translations, which I said you've seen before already. Remember the rotations, reflections, enlargements, and translations, okay? And this is what they look like in vector form, okay? Happy with that? Okay, good. I'm going to say a little bit more, okay? I'm not necessarily doing it in the same order as the chapter, but I'm trying to give it to you in an order that makes sense of it all as well, okay? Now, suppose I wanted to know what the actual size of this vector was. I'd normally use the word magnitude. I'd say, what's the magnitude of the vector? Okay, let's just get rid of this for the time being. Okay, what I mean is, what is that length there? That's what the size means. Can you work it out for me? Done it? Good. Can you see what that length there is? Well, this is a right angle triangle, isn't it? Okay, and what are you going to use? Exactly, Pythagoras Theorem. Okay, do you like that t-shirt? I actually bought it in Greece. Yeah, that's kind of special. So what you do is you'd write down 3 squared plus 6 squared, and then you'd square root that, yeah? So you'd have 36 plus 9, root 45, yeah? So root 45, and can you simplify that third for me? Root 45, that's root 9 times root 5, 3 root 5, okay? 3 root 5. Notation, what am I going to write down? Okay, I can either write this, OA, now written like that, that means the length OA. So notice the difference between that and that. Okay, that means the vector OA is that, and that's how you write a vector with the brackets. Okay, and that means it's a length OA. So it's important that you get the arrow on that notation if you write it as a vector, okay? Or alternatively this, okay? I'm going to write down OA, and the symbol we use for magnitude is this. They're called modulus brackets. Let me write that word once for you. They're called modulus brackets. They sometimes mean absolute value, okay? But in this case, they mean the magnitude, which is the size or the length, okay? So that, okay? Now suppose I wanted to work out this. Write it up. That means what is the magnitude of OB? If you've not done it, pause the video and quickly do it. Have we done it? So again, using Pythagoras Theorem, you've got 16 plus 4, yeah, which is 20, square root of 20, okay? Square root of 20 is square root of 4 times square root of 5, which is 2 root 5, okay? So the magnitude of that is 2 root 5, okay? What about the direction? How do you work out the direction? Maybe pause the video and figure it out, okay? So what we mean by direction is, okay, what is the angle here, which we commonly use as theta, between the vector and the positive x direction? Okay, that's what we normally mean. The angle between the vector and the positive x direction. Okay, and how would you work that out? Okay, well, you'd use trigonometry to do it. Okay, I'm sure you don't need this anymore. Okay, can I rub this off? So if you missed it, just rewind the video and make the note. Okay, that's the great thing about videos, isn't it? You can just pause, rewind, and just see it again. Okay, so to work out that angle there, theta, I'm going to do the inverse tan of 6 over 3. Remember, opposite over adjacent. 6 over 3 is 2. Now, I don't know that one in my head. So I get my calculator, so I'm going to put it into degrees mode, because I often have it in radians mode for the year 12, 13 stuff. So inverse tan of 2, okay, 63.4 degrees. Okay, so 63.4 degrees. Now, if I needed to, I could find that as a bearing, couldn't I? You know how bearings work? Okay, a bearing is always measured from the north. Okay, so I'd have that as the north, okay, and the bearing would be that. So what I'd do is I'd subtract that from 90 degrees, and my bearing would be, what, 27 to the nearest whole number. Okay, so that would be 027 degrees as a bearing from the north. Okay, I'm going to work out the direction of this. Now for this vector, the direction is that this time. It's always a direction from the positive x-axis. Okay, so that's the angle that I'm after. Can you work it out for me? You've done it? Good. I'm going to call that angle alpha this time. Okay, like this. We usually use Greek letters for angle stuff. Okay, so you'd have alpha is equal to the inverse tan, this time of, oh, I did not do that on purpose. Promise, I did not do that on purpose. Of kind of, same again, isn't it? Okay, well, that's kind of simple. Okay, so inverse tan of 2, which is 63.4 degrees. Okay, seriously, I just randomly put these things up, and well, there you go. So therefore, the direction, okay, like that is going to be equal to what, 180. Subtract 63.4 degrees. Okay, so that's going to be 116.6 degrees. Yeah, yeah. Okay, from the positive x-axis. Okay, does that all make sense so far? Okay, right. I've written out 4 different vectors here. Now I've used a different notation for this. Okay, now before I use the OA, OB notation. You use that when you're joining one point to another. We normal label points with capital letters, don't we? If you think about all the shapes questions you've worked on, the geometry, find the area of triangle ABC, for example. Those ABC are mentioned in capital letters, aren't they, for the vertices? Okay. When I write it like that, okay, letter A, that means that the vector 1, 2, which looks something like this, 1 unit right, 2 is upwards, okay, that there is represented by a vector A. What it means is I'm just not interested in what the actual points there are called, okay. Now if I draw that one there, 3, negative 4, okay, so that's going to be 3 units this time, and then 4 units downwards, like that, okay. So that's vector B. I can draw all of these out. Sorry, I'm not necessarily doing them in the right order. 0, 5, what does that look like? I'm going to put this one here, okay? So 0 means you don't move horizontally, you just move 5 upwards. So it's just going to be that. Okay, that is vector C. And 5, 10. Can you tell me what 5, 10 looks like in relation to one of these? Which one would it most look like? It's going to look most like this one, isn't it? Okay, so this one's 1, 2, and 5, 10 is going to look something like this, isn't it? I didn't even do the dash. I'll do it now, okay? So there we go. Yeah. So what have these two got in common? Vectors A and D. You see, they're parallel. Okay, I hope they look parallel anyway. They're supposed to be parallel. Okay, why are they parallel? Can you see? Because that is 1, 2, that is 5, 10. That is double that, and that is double that. Okay, or this is a multiple of this. Okay, when that is a multiple of this, a simple way of writing it is this. Rather than write 5, 10, I could write it as 5a, which equals 5, 10, of course. Okay, does that make sense to you? Okay, because knowing whether vectors are parallel is going to help us quite a lot later on. All right. Now we could work out the magnitude of all of those just using Pythagoras Theorem. Same as before. Do it again if you want, just as a practice. But Pythagoras Theorem, this. Obviously that length is just 5. Okay, and you can work out the directions as well. So directions. So there, and there. That one's below the x-axis, by the way. So you can denote it as a negative angle if you wish. Okay, but that's another way of labelling different vectors. Okay, now we can add vectors together. That's what we're going to do next. Okay, can you just think about this for me? What is this going to look like? A plus C. And notice I'm underlining these vectors because if I just wrote this, the A and C stand for algebraic letters. Okay, see this all over my t-shirt. Okay, they're all algebraic letters. Okay, whereas when you underline, they become vectors. What's that going to look like? A plus C. Okay. Well, you can do it one of two ways. Okay. One way of doing it is to write it like this. A is 1, 2, and C is 0, 5. Add those together. You add the horizontal components together, 1 plus 0, and the vertical components together, 2 plus 5, 7. It's a bit like adding x and y coordinates together, really. Okay, you get 1, 7. And then you can draw that out. Okay, 1, 7 looks even like this, doesn't it? 1, and then 7, something. So it looks something like that, doesn't it? Okay, and I'd label that as vector A plus C. Okay. Alternatively, what I could do is I could do the diagrammatic approach, which is start with 1, 2. Okay, so 1, 2 is this 1, 2. So that is vector A, like that. And then on top of that, at the end of that, put in vector C, which is 0, 5. So starting from here, 0, 5 is this. And that's vector C. And notice what I get with my end result is exactly the same as that. Okay, there's two ways of doing it. So the way that vector addition works visually is you draw that vector first and you draw that one on the end of it. Okay, and that's basically what vector addition is. Okay, now I want to turn to that bit again. Okay, the fact that D is equal to 5A. Okay, that 5 is what we call a scalar. In other areas of maths, we call it a constant. Okay, in vectors, means the same thing, but we call it scalar. Important word. Make sure you make a note of it. Okay, a scalar is just a constant. Okay, it's just a value. Okay, so what that means is that if I multiply a by a scalar value, I'm saying I'm going to multiply a by something. Can you work out what that is? Of course you can. Okay, 7 times a just means you do 7 times 1, 2, which is going to be 7, 14. Okay. And that's what it is, okay? Is this going to be parallel to A? Of course it is. Of course it is, okay? We tend to use a Greek letter lambda, okay? I don't know if that's somewhere on here, okay? Pythagoras Theorem, no, and I can't quite see it, no, unless I missed it. It's difficult for me reading upside down, okay? But yeah, we often use a Greek letter lambda to represent a scalar in vectors work, okay? So if I say the scalar multiplied by A, okay, what that means is this is any vector that's parallel to A. That's kind of important, okay. If I want to use a different letter, I might use a Greek letter mu, okay, because it follows in the alphabet LM, lambda, mu, okay. If I have mu times by B, what I'm interested in is a scalar multiple of B, which means a vector that's parallel to B, okay. Just a simple example, that value mu could be 3, okay. So what is 3b going to be? 3 times that, which is 9, negative 12. Okay, and you can see how that works. Any numerical multiple, any scalar multiple, is going to result in another vector that's parallel to it. Okay, I'm going to stop there because that's a little bit more to digest, isn't it? Okay. I'll go through question 7 for you of exercise 1. All right, so that's on page 232. If you've not done it, maybe just have a go at it first and then replay the video. All right. So the points A, B, C and D are vertices of a quadrilateral where A has coordinates 3, 2. Okay. Now, when it says draw on squared paper, you don't need square paper, but I guess it kind of helps. Okay. You don't need the coordinate axes, but I've done it for this question in case it helps you. Okay, but you can do it without it. Okay. But A has got coordinates 3, 2, so I'm going to put that somewhere there. Okay. You do not have to be accurate with this. You see, it's just a blank board. I'm not being accurate. Okay, because we're going to do it mathematically as opposed to using the accuracy. Okay, you'll see what I mean by that later. Okay. Now, it doesn't tell you the coordinates of the other points, but it tells you some vectors, and we can use that to help us out. It tells us that AB is 2, 3. AB is 2, 3. What that means is from A to B, it's going to be 2 units to the right and 3 units upwards, isn't it? Okay, so I'm going to put B there. Okay, can you work out the coordinates of point B from that? Okay, yes you can, because if A is 3, 2, if AB is 2, 3, so 2 towards the right, the x coordinate will be 5. Okay, and then 3 units upwards, the y coordinate would be 5 as well. So that must be the coordinates 5, 5, mustn't it? And I'm going to write B a bit like that because it's just a bit neater. Okay, does that make sense? Okay. By the way, if you look at the answer in the back of the book here, it's not quite right. You'll see what I mean if you check it out, but it's not right. Okay, so that's point B. All right. Then it says B to C is 3, 1. So you can see what we can do here. Starting with B, from there to C, it's 3, 1. So it's 3, 1, somewhere like that. Okay, that's point C. Can you work out the coordinates? Again, yes, you can. Okay, so 3, 1 means 3 towards the right. So 5 plus 3 is 8. And then 1 unit upwards, 5 plus 1 is 6. So that must have coordinates 8, 6. Okay? And then C to D is negative 2, negative 3. So C to D is negative 2, negative 3. So it's somewhere like that. Okay? And can you work out the x coordinate and y coordinate? Yes, you can. Okay? So 8 subtract 2 gives you 6. And then 6 subtract 3 gives you 3. Okay? So you've got that. Then if you want, you can draw out your quadrilateral. Okay, you can draw out your quadrilateral. And there it is. A, B, C, D, and then join it up like that. And that's it. That's your quadrilateral. Okay? Right, next it says, write AD as a column vector. Okay, so this is part B. Write AD as a column vector. So that's from here to here, isn't it? Okay, you can use the coordinates to do that. So how do you get from 3, 2 to 6, 3? We go 3 units towards the right, so that's 3, and then 2 units to 3 units, that's 1 unit upwards. So it's 3, 1. Okay, good. What type of quadrilateral is ABCD? Okay, well don't guess it. Okay, don't guess it. What you should do is this. Okay, you should consider what all of these vectors actually are. Okay, I'll put my book down. I don't know why, because I'm going to pick it up again. Okay. But it tells us this, doesn't it? It tells us, I'm going to write this one down first, this is an interesting one. It tells us BC is 3, 1. That's really interesting, isn't it? You should find it interesting. Okay. What can you say about AD and BC? I know not just that they're the same vector, they're the same length and they're parallel. With shapes, that's really important. Okay. AD, so that's that one, is parallel to BC, that's that one. That's going to help us, isn't it? Okay, because imagine, like me, you're not drawing it all accurately to scale. No, those two sides are parallel. It's going to be helpful. Okay, so it's going to tell us something about the actual shape. Okay, and then I'm going to write down what the other ones are. So AB is 2, 3. So let's write that down. AB is equal to 2, 3. And it also said CD was negative 2, 3. Okay, well look, I'm interested in AB and, to be honest, DC. Okay. So if you don't mind, I'm sure you don't mind, do you? I'm going to write DC. Do you know what vector DC is? It's the other way around. It's also 2, 3. But you notice when they say CD as a vector, it means that way. Notice I put the arrows on my lines here. They're to indicate not only that they're parallel, but to indicate the vector AB is like that, and DC is also like that as well. Okay, that's going to help us answer the question, isn't it? Okay, you've got the opposite sides are parallel, And they're equal in length. They've got to be equal in length, okay, because they're exactly the same vector. What shape has opposite sides that are parallel and equal in length? It is a parallelogram. Yeah, a parallelogram. There we go. What if you didn't know that the sides were equal in length, okay? Well, you can work it out, okay? Use Pythagoras Theorem to do it, okay? You can work out what the length of that is. Can you do it for me? Root 10? Can you do it as quick as that? Okay? 3 squared plus 1 squared, 9 plus 1, root 10. Can you work out what that is as a length? Okay, do it for me. Root 13, root 4 plus 9, root 13, okay? So that's root 10, okay? Let's just write this down, shall we? AD has got a length, root 10. I've worked out that AB has got a length of root 13, okay? Because that's the same, okay? Root 4 plus 9, root 13. And because that's the same as well as that, that's going to be root 10. So you can see if I label up the lengths of the sides, that shows you that's a parallelogram, isn't it? Sometimes in harder questions, you need to work out the lengths to show that it is maybe a rectangle or a square, okay? Or even isosceles triangles. Those sorts of questions come up as well. If you've got an isosceles triangle and you prove it's isosceles, you've got to show that 2 sides are the same length and the other side, the third side, is not the same. Or an equilateral triangle, or whatever shape you want to look at, okay? Lengths are in there somewhere, okay? But Pythagoras Theorem is the method. You don't have to do much with angles, okay? You'll be pleased to hear, because we get the sense of direction from the actual vectors themselves. So I'm hoping that kind of makes sense, okay? Is there anything else? Part D, what do you notice about BC and AD? There and there, well, they're the same vector, okay? But as I mentioned, not only are they the same vector, you can say that these two are parallel and equal in size, okay? I'm hoping that was helpful to you.